Good afternoon, good morning, everyone. Depending on where you are. Um, I believe I have the go ahead to get started. I'll go ahead and do that. Thank you for attending this talk. My name is Andrew Yule, and I work at a company called Ponsum Analytics. I'll talk about Ponsum here in a minute. But the point of this talk is to discuss how I used Wolfram Language and some of its, particularly some of its machine learning prediction capabilities to help implement a real-time uh, monitoring solution for hydrate risk in an FLNG or in an LNG facility. So I will jump into that. Um, a real quick kind of an intro into Quantum Analytics, the company that I work for. We are a specialist consulting company, and we focus on combining um, basically engineering with data-driven analysis. We're kind of a unique group of employees. We've got strong backgrounds in engineering, chemistry, and then data science, and we kind of use all those tools that we have to solve problems for our clients. In terms of kind of the areas that we operate, I'll actually kind of go this bottom up here. We have some work that we do in the industrial space around kind of predictive analytics and predictive maintenance and things like that for large industrial applications. We do a small bit of things in the performance space around computer vision and tracking motion and things like that for optimal human kind of movement and less injury. We do a little bit in the health space. Similar idea was kind of what can you do with data around preventing illness and kind of increasing longevity, things like that. We have some assets that we own in the mineral space, and then kind of our main focus or what we do more than anything is focused in the energy space. And so there again, as I mentioned, we're kind of by background. We have the a strong expertise in engineering, chemistry, so things like production chemistry, understanding fluids, things like that, and then tying all that together with both physics-based modeling as well as data-driven modeling, things like machine learning and things like that. So it's kind of the areas that we operate in. Uh, Kind of coming off the back end of that, where we operate, where we focus a lot of our work is in the offshore oil and gas environment. And so in that space, you're dealing with very extreme conditions as far as your temperatures and your pressures. Just kind of for reference, if you're producing uh, hydrocarbons from the bottom of the body of water like the Gulf of Mexico, you're trying to get those hydrocarbons from the ground, which could be 15 to 20,000 feet below the surface, and you're sitting in around 8,000 feet of water on top of that, right? So the pressures of that water sitting on top of that, and the temperature that you're dealing with can cause all kinds of issues with the fluids that you're trying to produce. One in particular issue that we routinely have to deal with and mitigate and provide strategies for how you avoid is something called hydrates. So hydrates are a unique structure. They're actually what's called a clathrate compound, and when you have ice, when you have water in the presence of a hydrocarbon gas like methane, ethane, things like that, what happens is that those gas molecules can get trapped by the water, and the water will typically kind of form this cage-like structure around those molecules, um, and they become very problematic for your pipelines. I've got an example here on the right here. So you can form these hydrates in your pipeline, and if you have enough of the right conditions and enough of the mass required, the water and the gas, those hydrates will continue to agglomerate together, and they'll basically lead to a blockage of the pipeline. And if you can imagine, in an isolated pipeline subsea, that's an incredibly problematic situation. So um, I wanted to give this background about hydrates because it's going to feed into what we were doing on this particular project. So a little bit more just about kind of hydrates and why they're interesting. So they obviously they look like ice, right? They kind of they feel like ice and things like that uh, as you're looking at them. But you can see here. So I've plotted this is a temperature versus pressure plot. The blue line here is actually ice, right? So water ice forms at 32 degrees. As you increase the pressure, there's a small deviation where you can actually go a little bit lower before you start to form ice. So kind of to the left of this line is ice, to the right is no ice, right? Now, hydrate curve is actually this red line here, right? And what you can see is that you can form a hydrate at temperatures well above freezing, and actually at temperatures that are relatively moderate, somewhere around 60 to 70 degrees if you have the pressure, right? So there's a strong pressure component, and that's what ultimately allows hydrates to form in situations that you wouldn't necessarily intuitively expect a hydrate to form if you thought about it like ice. So that's some background about hydrates. What I wanted to focus on now is actually the project that we were involved in. So this was not an offshore project. It was actually an onshore LNG facility. And so LNG stands for liquefied natural gas. So what you were doing in LNG, I'm sure most people have heard of this. You probably see it on the news occasionally, things like that. It's essentially you're taking methane, right, which is a gas, and you're converting it into a liquid form so that you can transport it easier, right? So we've heard of like exporting LNG. That is essentially where you're taking this methane, you're converting it into a liquid form, and then you're able to ship it on these large tanks kind of around the world. And it's one of the most effective ways to transport gas. The process of actually creating LNG is rather difficult, though. Methane by itself does not want to be a liquid, right? At really at any temperature that we're used to, right? So this again is kind of that same plot I was showing earlier, but this is temperature versus pressure, but this is the phase envelope for pure methane, right? So basically at temperatures above around minus 300 degrees Fahrenheit, that methane is going to want to exist as a gas. So the only way you can get it to a liquid to actually cool it is to actually cool it down to these temperatures. So you typically see LNG plants operating at around minus 260 degrees Fahrenheit. That's the only way that they can get that ethane into a liquid form. Now, one of the other things that occasionally these plants will do is they will also include an ethane stream in there, right? So methane is a single carbon molecule, so carbon and four hydrogens. Ethane is two carbons and six hydrogens. Yeah, and so what you end up with when you do that is you can increase the heating value of that methane that you're shipping. And all of the LNG prices and things like that are generally they're costs based on how much heating value you actually have. So if you have ethane available as a source for you, you can inject that into the methane, then do your cryogenic processes, and you actually increase the heating value of that LNG. So here I've got that same methane phase envelope, and here I've got the ethane phase envelope, right? And you can see ethane is much more likely to form. Over here it will be a gas, but at relatively reasonable temperatures, you can convert ethane into a liquid, much easier than you can with methane. So now, when you inject that ethane, which in the case of this project was coming in as a liquid stream because it was at a higher pressure and slightly cooler temperature, right? Now you have a methane and ethane stream, and you actually have a multi-phase or a multi-component system, right? And so the phase behavior of that system is fundamentally different from when you have either methane or ethane together. You can see here, this is a representative phase envelope for what a 80-20 mixture of methane-ethane looks like. Right, so you can see that we shift ethane, we shifted to the right compared to methane, we're shifted to the left compared to ethane. And we also have this envelope, right? And what that means is that in between these two bands, we'll actually have kind of a multi-phase, where we'll have a liquid and a gas phase present at the same time. The important thing, though, is that when you're injecting that ethane, you're injecting it as a liquid state, and when it mixes with that methane, there's a vaporization process that's going to happen to that ethane. And through that vaporization process, the ethane will cool, right? And sometimes that cooling could be quite substantial. And so this kind of tying this back to what I was talking about earlier, if that cooling is substantial enough and you actually have some moisture content in either the ethane or the methane stream that you're mixing, you suddenly have a risk for forming hydrates. So same idea that I was talking about before. Now in this case, these streams that we're mixing when you're going into an LNG facility generally are very pure. They've already gone through some kind of processing, or some kind of separation of different components within their streams. However, there's still a strong chance that you'll end up with enough water content in those streams to actually form hydrate. Generally, when you're looking at forming hydrates, you're in a situation where you have excess water. So water is not a limiting component to the hydrate formation. However, in this case, because we are at such low water contents, the conditions that you'll form hydrates at are actually limited by how much water you can form. And some of the theory and some of the calculations that have been testing that are out there show that there's a bit of uncertainty at these kind of conditions. So for example, I've plotted here. You can see kind of moving from the right to the left. You can see how that hydrate curve that I was showing originally, how that changes as you move on the far right. You're saturated with water. You have enough water that you're not limited in the hydrate formation on water. And as you move down to smaller and smaller amounts of water, you can see that curve starts to shift to the left. As part of this project, we did some testing of running some experiments at a water loading that was kind of somewhere in that middle range there, and you could see we ran multiple tests on multiple tests at multiple conditions, and you can see the error bars there were somewhere around 8 to 12 degrees Fahrenheit, right? So this says that there's an 8 to 12 degrees margin or uncertainty on what the actual hydrate formation conditions are when you're in this water limited situation that we're trying to monitor. Okay, so jumping kind of into the heart of the project and what we were given and what we were looking to do. This first image here is an actual a drawing of where this mixing takes place. Right, it's actually a relatively simple piece of equipment. It's a long pipe about 20 feet long, pretty substantial diameter. There's two injection nipples up here on the top, and this is where the ethane streams come in. So the ethane rates are we've got equal liquid rates of ethane coming into each port up here. The mixing happens, and kind of by the end of this, you've got a kind of a homogeneous gas phase of your original natural gas with that vaporized ethane. As part of the project, there were some really interesting computational fluid dynamic simulations that were run to kind of understand this process in detail. So what I'm showing here is you can see that you've got your natural gas coming in at around 71 degrees Fahrenheit. These ethane streams are also coming in around 70 degrees Fahrenheit. Now that mixing happens, and it happens relatively quickly, but during that initial vaporization, you can see that you get some ethane coming in here, and you get temperatures dropping to around minus 32 degrees or so. Now, only around 5 to 10 feet down that line, you can see that all the temperature, all the mixing, the full mixing has occurred, and you're back up to the temperatures around 40 degrees Fahrenheit or so. So there is a strong risk of kind of what might be happening here when you're forming those incredibly cold temperatures for a brief period of time. And the key thing that we wanted to analyze and look at is, are you forming those cold temperatures as close to the center of the pipe as possible? Because if you're forming those on the outer walls of the pipeline, you're giving a spot for hydrate agglomeration to occur. And if you're doing this with kind of mass volumes that are being injected into this pipe, you're just continually feeding that hydrate formation, and it wouldn't take long before the agglomeration process would become large enough that you could cause a blockage in this, right? So the thing we wanted to make sure is that this process, you're going to hit these low temperatures, but it's going to occur as close to the middle of the pipe as you can, and then very quickly we start to seed all that phase mixing, and you end up with a much warmer process, right? So this detailed simulations were performed to just understand and validate the design and look at the detailed fundamentals of what was going on. Once we ensured the design was fit for what we needed it to, we could take a step back and take a more traditional approach that didn't involve computational fluid dynamics, and instead use just a normal process modeling approach. So here we've set up a simple model in a process simulation around this whole process. And the speed here of how we can model with this is orders of magnitude faster than what we can do with computational fluid dynamics. And so this gives us the ability to basically change inputs, right? Change all the inputs that we care about in the model. So that's, the temperatures and the pressures and the flow rates of both the ethane streams and the methane streams, the compositions, the water contents, things like that. And then ultimately what we wanted to do was to monitor for this hydrate risk after all this mixing has occurred, knowing that this process model that we've set up here has been validated by the more computationally heavy approach up here. So all in all, we ended up with a HYSYS model that was capable of simulating 200,000 cases, right? And we set this up in a parametric study, like I said, varying all the possible inputs that we care about that could change within the system. So, kind of just recapping where we are at, right? So we've defined the risk for the project, right? There is a risk of hydrates that we want to completely avoid, right? We don't want that risk to be present while we're operating. We defined what the ideal margin was that we need to stay above. Again, from some of that lab testing, we know that there's an uncertainty around 8 to 12 degrees Fahrenheit. So if our prediction was, as best as it could be, we could still expect that there's 8 to 12 degrees of uncertainty. So we want to operate around whatever our prediction is, essentially plus 8 to 12 degrees of margin of uncertainty to ensure that we do stay outside of that risk for hydrates. There was detailed CFD modeling done to simulate this process in detail. And once we understood that, and we could then build a faster process simulation model that was ensured to be aligned with what we'd done on the computational fluid dynamics approach, right? And so at this point, the client said, what we would like to be able to monitor is our hydrate formation margin in real time to alert operations whether they need to cut the ethane injection or stop it altogether, right? So I'm getting to now the part where Mathematica and Wolfram Language actually came in. So we ran this large parametric study in HYSYS. Again, we have over 200,000 data points of all the possible ways that this system could behave. And we were tasked with how do you build a model that can be implemented into a real-time system to predict that hydrate formation temperature for the client. So the first thing we did with the Wolfram language was we put all this data in and we used some of the predict functions, right? And what that did is that gives us a really easy starting point to say, okay, what kind of accuracy can we achieve with relatively simple models, like something like a linear regression, and then increasing in complexity to something like a neural network, and then ultimately, right, because this is a parametric model run from a simulation, we controlled the inputs. So we have essentially a squared off arrays of inputs that we're putting into this, so you can actually use multilinear interpolation here, right? And that actually ends up being the most accurate way that you can model this. But the problem there is if you want to embed something like that into a relatively simple automation control system, you're talking about being able to take all 200,000 of those points and put them into the model, right? So where we kind of compromised was on, okay, let's look at this neural network approach, right? The linear regression model, it just doesn't have the accuracy we need, especially if we're looking at 8 to 12 degrees of margin on our results. If we're seeing that in the error alone, it's not going to be feasible, right? The neural network looked like it had the highest levels of accuracy right out of the box, and we figured that maybe there was a good way that we could tweak some of that to improve it further. So again, we used the Wolfram language, building a relatively simple neural network with 3 different linear layers and some ramp functions for the activations. We were able to achieve basically the following results down here, right? So this is a parity plot showing how our predictions for the hydrate margin with this neural network compared to the actual predictions from HYSYS model. Our overall mean absolute error was around 0.207, and the root mean squared error was 0.306, right? So very good performance, probably within what we would want for this type of model to be deployed into the field. And so with that, we kind of set out to do that. So we said, how can we most easily put this neural network into practice in the field, right? We don't have the ability to call web APIs and things like that, so we can't deploy this model into the cloud. So here again, what we were able to use is some of the net extract functions in the Wolfram language to pull out those weights, the biases, and things like that. And then we could actually construct the matrix multiplication operations that the neural network was doing. And we worked with the automation control to get all of that math programmed into the automation control. So got a little screenshot here, but you can see this is the real life system, right? It's receiving its data in real time and all that. And then right down here, we've actually got our model kind of running in the background, telling them what the hydrate formation temperature is and what the hydrate margin is. You can see here, it's around 48 degrees, so kind of well outside of where we would want to be during during steady state for some kind of hydrate monitoring risk. So, yeah, so just recapping, right? So kind of where Wolfram Language played a role, right? We actually analyzed years worth of historical data. I didn't get a chance to talk about that, just time and things like that. But it was a big component of understanding the possible risk in this system. Once we knew once we had this process model, we knew what conditions were going to be problematic, and we looked at historically, do we ever kind of reach some of those conditions? And it turns out that we do. Not that often, but it certainly was a risk for the facility and something to be planned for. The Wolfram Language also allowed us to use very easy screening of different models to give us a place to start with before just diving into something more specific. Then the neural network framework within the language is very easy to use. It's very flexible. It's a lot easier than some of the more traditional languages out there when you're trying to build these neural networks. It also gives us the ability to kind of write scripts, right? So I mentioned one of the neural networks that we built for this project. There was actually two more, and I didn't want to spend too much time on them, but we were able to build those in a very automated fashion using just normal code that's in the Wolfram language. And then lastly, the symbolic architecture of language, right? It makes it so much easier to pull out the information that you want from those different layers that you've trained. Things like that. It's all things that can be done in other languages, right? But it's the consistency and the cohesiveness that's in the Wolfram language that allows it to be this kind of one-stop shop for executing a project like this and seeing it from start to finish. So that is all I have. Let me quickly jump over here to let's see if there are any questions. Not seeing any, so yeah, that's it. Thank you all very much for attending.